Hello all, in this lesson we are going to be studying mixtures, distillation procedures and setup, and distillation theories and logic. There's no homework associated with this lesson, but for the first item on your classwork page I would like you to copy down the same. How can you separate mixtures in a solution? And also add it to your graphic organizer for essential questions. And following that, copy down these questions, which we will answer as a do now in class when I see you next. Okay, mixtures. A mixture is defined as a homogeneous mixture or a heterogeneous mixture, and those two things are different. Homogeneous mixtures have extremely evenly distributed particles. I'll underline that. And heterogeneous mixtures are not evenly distributed particles. So the examples I have up here are this beaker with a colored solution in it is going to be considered homogeneous because of the even distribution of the particles. But a salad is also a mixture. It's just that it would be considered heterogeneous because of the unequal distribution of particles. Gases like air, for instance, are a very homogeneous mixture of the different gases that make up air, like nitrogen, oxygen, carbon dioxide, etc. And then pizza would be a heterogeneous mixture because of the uneven distribution of particles. So basically, whenever you see the word solution, such as a saltwater solution or alcohol and water solution, you should think that these are homogeneous because the particles in those solutions are extremely evenly mixed. But pretty much all other types of mixtures that you can think of that are not solutions are, for the most part, heterogeneous mixtures. So one of the more creative tasks that the Regents may ask you to do is how to separate mixtures, whether homogeneous or heterogeneous. Now, heterogeneous mixtures are a little bit easier to separate, and we will cover most of the processes for separating heterogeneous mixtures tomorrow. But today, there's a process that you can use to separate homogeneous mixtures, those ones that are really evenly mixed, which is requires a bit of a setup, and it requires basically all of this equipment. We don't even have access to this equipment in our lab, so we can't do it for lab, but I can explain it enough that you will understand how it works. It's called distillation, and you definitely take great notes about this one. But you have some very basic sort of science equipment, such as a round bottom flask. And inside that flask, you typically have some kind of homogeneous mixture that might even be referred to as miscible. And miscible means that you can mix the ingredients of that mixture in any ratio. For example, if you have a little bit of alcohol and a ton of water, those two things will mix together perfectly. Or opposite of that, you could have a little bit of water in a ton of alcohol, and that would mix together perfectly as well. So miscible just means two liquids that can mix in any ratio. So we've got that. And we have a thermometer up here, which is going to help us monitor boiling points. And to the right of that, we have this guy, which has two names. It could be called a condensing tube, or it could be called a water jacket. When you call it a condensing tube, you're referencing the fact that you have vapors coming up from the boiling liquid in the flask. They're coming down this tube, and when they encounter this tube, they'll condense back into a liquid and drip into this flask, drop by drop. So that's why we sometimes call this a condensing tube, but I like to call it a water jacket, and it's because of the way it's made. You have cold water coming in here, and it flows around the outside of the tube, and then exits the tube here and goes into some kind of a waste container, like a sink or something. But it makes the inside of the tube really cold because it has cold running water running around the outside, and that will allow the condensation to take place. And the last flask down at the bottom is called an Erlenmeyer flask, and it's what collects something called the distillate, which is the product of distillation. So, in short, what you've got here is some kind of homogeneous mixture that you want to separate. You apply a heat source via a Bunsen burner, and it brings it up to a boil. Now, depending on what's in the mixture, if they have two different boiling points, like alcohol and water do, then whichever one has the lower boiling point will start to boil first. You can keep track of that by using the thermometer, so you know what the temperature is. And so yeah, the one with the lower boiling point boils first, it comes up, the condensing tube condenses it into a liquid, it drips into the Erlenmeyer, and once you've boiled away all of that first substance, what you have in the Erlenmeyer is the substance with the lower boiling point, and what you have left in the round bottom flask is the substance with the higher boiling point. And what you've done is you have separated two substances that were in a homogeneous mixture based on a property that they have, and that property is really simple. It's boiling point. So you can separate particles based on boiling point. So this process could be used for two liquids, two miscible liquids like alcohol and water, or it could be used for a dissolved solid solution such as salt and water. Inside the round bottom flask, that's where you have the mixture that's boiling, and the lower boiling point one boils first. And from there, that lower boiling point liquid goes up to the condensing tube where it turns back into a liquid from its vapor state. And now that it's in its liquid state again, it drips into the Erlenmeyer flask, which collects the distillate. Alright, so let's just make sure we can nail down the theory and logic behind distillation. Distillation does rely on the fact that different substances have different boiling points. Otherwise, it simply wouldn't work at all. So for example, if I were to heat two mixtures, or excuse me, a mixture of two substances, A and B, both of which had a boiling point of 300 Kelvin, then if I were to raise the temperature inside the round bottom flask to 300 Kelvin, both substances would boil simultaneously. Then they would both reach the condensing tube at the same time, and they would both condense back into a liquid together, and what you would collect in the distillate is both A and B. In the round bottom flask, you wouldn't have anything left. And so you would have done a very poor job of separating the mixture of substances A and B. Alternatively, if you heated two mixtures A and B, A which boils at 300 Kelvin and C which boils at 2760 Kelvin, then when you raise the temperature in the round bottom flask to 300 Kelvin, only substance A would boil. The distillate then would collect substance A versus substance B. And in the round bottom flask, you would only have B left. Alright, we made it to the pair up. Please copy down these questions underneath your aim and do now. And then underneath the pair up, please copy down these summary questions. So you should have Cornell notes for distillation and mixtures, and you should also have a separate page that we'll use in class tomorrow. Thanks for watching.